Alzheimer's disease was first described by Dr. Alois Alzheimer as timeless dementia. This disease is an unclear neurodegenerative disorder, and effective treatment has not been developed to date. Dr. Alzheimer described the presence of amyloid plaques and neurofibrillary tangles in the patient with Alzheimer's disease, and raised an important hypothesis explaining the pathogenesis of this disease, amyloid cascade hypothesis. According to this hypothesis, amyloid precursor protein can be cleaved in two different ways. In the first way, amyloid beta peptides are not released into the environment as the final product. The first enzymatic cleavage is performed by alpha secretase in amyloid beta domain, and the second enzymatic cleaved reaction is observed. This way is called as non-amyloidogenic pathway. In contrast to this way, the first enzymatic cleavage is provided by beta secretase, which is also known base 1 in amyloid precursor protein. And C99 peptides are released into the environment. Released C99 is cleaved by gamma secretase, and amyloid beta peptides are released into the environment. This way is called amyloidogenic pathway. According to amyloid cascade hypothesis, released amyloid beta peptides aggregates to produce oligomers. These aggregations fall down in synapse and prevent synaptic transmission. Further aggregation of these oligomers form senile amyloid beta plaques that activate microglia. Activated microglia release inflammatory mediators, which trigger mitochondrial dysfunction and oxidative damage in neurons and glial cells. All this damage lead neurons to programmed cell death pathway. In this review, one of the studies placed at the center has been conducted by Pignatelli et al. They indicated that the excitability states of engram cells involved in the memory recall process are increased. Moreover, to enlighten the underlying mechanism of this engram excitability, they evaluated the sensitivity of engram cells to the inward rectifier potassium channel using blockers. And they found that blockers significantly reduced inward currents in the dentate gyrus granule cells. So, blocking potassium channel suppressed memory retrieval. Based on these grounds, we suggest that the optogenetic manipulation of serotonergic system will increase the engram function and induce retrieval of lost memory. Because it has been indicated that the injection of serotonin to the cell body leads to prolonged or complete closure of potassium channel on neurons. Consequently, the closure of potassium channel by serotonin increases the action potential, calcium inflow, and neurotransmitter release and excitability of engram cells. To test this hypothesis, fear conditioning protocol described by Ryan et al. Can be used. According to this protocol, light electroshock is applied to the feet of a transgenic mouse model of Alzheimer's disease. Then anisomycin, a protein synthase inhibitor, is injected to delete the fear memory associated with the cage B in mouse brain. It is then put back into cage B to test whether mouse still has the memory of electroshock. After that, serotonergic neurons that project to memory engram cell store fear memory in dentate gyrus are artificially stimulated by the optogenetic techniques in cage A. Consequently, serotonin's role in retrieval of lost memory is confirmed when behavioral sign of fear memory is observed. To our knowledge, this is the first study that raises potential interaction between serotonin and engram cells. Literature indicates that testing the effect of serotonin receptor on engram cell excitability using modern electrophysiological and optogenetic tools could be